All right, so we're going to start the multiplication rule and the conditional probability rule. We'll also talk about independent events in sections 5.3 and 5.4. There's a definition there. It says the conditional probability of event A given event B, which is denoted by A given B, is how I read that, is the probability that A occurs if we know that B has occurred. Okay? The general multiplication rule says for any two events, A and B, the probability of A and B is equal to the probability of A times the probability of B given the fact that A has occurred. Let's take a look at problem 26 here. So it says that suppose that two cards are randomly selected from a standard 52-card deck. Part A, what is the probability that the first card is a club and the second card is a club if the sampling is done without replacement? Okay, so I'm not going to put the card back in the deck. I need to find the probability of selecting two clubs. Well, there's 13 clubs in a deck, so 13 over 52 would be the probability of selecting one club. Now I need the second card to be a club. Okay, now if I've already pulled a club, well, there's 51 cards left in the deck, right? And if I've already pulled a club, there'd be 13 clubs still left in the deck. So 12 divided by 51 would be the next probability that I'd want to multiply this by. Let's see, 13 over 52 reduces to 1/4. 12 over 4 is 3. And 3 over 51 reduces to 1 over 17. So 1 over 17 would be the answer to that. Okay. Part B, what is the probability that the first card is a club and the second card is a club if the sampling is done with replacement? Okay. So the probability of getting two clubs with replacement. So I'm going to select a card, I'm going to look at it, and then I'm going to put the card back in the deck. Okay, and I'll shuffle and then I'll select another card. So what's the probability that I get two clubs? Well, 13 over 52 is the probability that I get one club. Okay, now that card's going back in the deck. So there's all 52 cards are there, hence all 13 clubs are still there. So I'd want to multiply by 13 over 52 again if I need that second card to also be a club. 13 over 52 is 1/4, so I get 1/4 times 1/4, which is 1/16. And 1/16 will be the answer then. There's a note here. Always assume that the sampling is done without replacement if you are not told that in the problem. Okay, so never assume that the card is going back in the deck or anything like that unless you're told that information. Okay. So, you know, and by the way, just to tie this in, so whenever you're selecting multiple items from a bag, a box, a deck of cards, whatever, always it's going to be the multiplication rule if you're selecting multiple items, okay? So, and is a key word, okay? So I need the first card to be a club and the second card to be a club if I need two clubs. The probability of B given A is the fact that I've already selected, you know, in this problem here, I've already selected one card that is a club. Okay, so I need that next card to be a club. So given that information, what's the probability that next card is also a club? Okay, that's what I mean by this notation here. Problem 27 says that a local golf store sells a bag that contains 35 golf balls in it. Suppose that the bag contains 20 Titleists, 8 max flies, and 7 top flights. And I'm using abbreviations there. What is the probability that two randomly selected golf balls are both Titleists? Okay, so the probability of two Titleists was 20 Titleists in the bag. The bag is 35 golf balls total. If I take 20 plus 8 plus 7, that's 35. Now, the next ball has to be a Titleist. Okay, so if I've already selected one ball from the bag, there's 34 left in the bag. The next one needs to be a Titleist also. So I've already pulled a Titleist. So there's 19 Titleists left in the bag. Or 19 over 34 would be the multiplier there. Okay, if I take 20 divided by 35 times 19 over 34, I get roughly 0.319. Okay, so there's a 31.9% chance that both golf balls will be Titleists. is what I conclude from that. Part B, what is the probability that the first ball selected is a Titleist and the second is a max fly? Okay, so it's got to be in that order. Well, 20 over 35 would be the probability of getting a Titleist, and you need the next ball to be a max fly. So if I've already selected one ball from the bag, there's 34 left in the bag. All the max flies are still there though, right? All 8 of them. So I'd multiply by 8 over 34. And by the way, you can just multiply straight across here. So 20 times 8 and 35 times 34. And that gives you roughly 0.134. Okay, so I got roughly a 13.4% chance of selecting a Titleist first and then a max fly second in this problem. Part C, what is the probability that the first ball selected is a max fly and the second is a Titleist? So here I've just switched the two events. Okay, so I need a max fly first and a Titleist second. 8 over 35 would be the probability of getting a max fly. And once I've selected a max fly from the bag, there's one less golf ball in the bag. And all the Titleists are still there though, right? All 20 of them. So I'd multiply by 20 over 34. Now, when I compare this guy to what I just did, all I've done is switch the numerators. So the answer is actually going to be the same thing, roughly 0.134. Okay, so there's a 13.4% chance that I would select a max fly first and then Titleist second. Part D says, what is the probability that one is a Titleist and the other is a max fly? Okay, now Part D is different from what they're saying in Part B. Okay, because Part B, they've indicated in order. Part D, they're not. Okay, so I have to think of how it can happen where I select a Titleist and a max fly. Well, I could select a Titleist first and then a max fly second, or I could select a max fly first and then Titleist second, right? Either one of these two options means that one's a Titleist and the other's a max fly. Or is a key word. Or means add. And by the way, I do have mutually exclusive events because I can't select one ball from the bag and have it be a Titleist and at the same time a max fly. That's impossible. Right? So I would just add these two probabilities together. And I've computed those two probabilities here in parts B and C. So if I take 0.134 plus 0.134, roughly, 0.268 is the answer. Okay. Here's an addition rule problem. They didn't have the word or anywhere in the problem, right? That's something I got to think of on my own now. Okay. Problem 28 says, due to a manufacturing error, 3 cans of regular soda were accidentally filled with diet soda and placed into a 12-pack. Suppose that 2 cans are randomly selected from the 12-pack. Part A, determine the probability that both contain diet soda. Okay, so the probability of getting 2 diets. 3 out of 12 would be the probability that 1 can is diet. Okay, now if I've already selected a diet from the 12-pack, there's 11 cans left in the 12-pack. 2 of them left are diet soda. Okay, so I multiply by 2 over 11. And let's see, 3 over 12 is the same as 1/4. And 2 divided by 4 is 1/2. 1/2 times 1 over 11, that's 1 over 22. 1 over 22 in decimal form is approximately 0.045. Okay. Part B says, determine the probability that both contain regular soda. Would this be unusual? Okay, well, so there's 9 cans that are containing regular soda in the 12-pack. 3 of them do not. Right, so 9 over 12 would be the probability that 1 can contains regular soda. Now I need a second can to also contain regular soda. So if I've already selected one, then there's 11 left in the 12-pack that contain regular soda. 8 of those 11 cans contain regular soda. So I multiply by 8 over 11. 9 over 12 reduces to 3/4. 8 over 4 is 2, so 3 times 2 gives me 6. I still got the 11 in the denominator. 6 over 11 is the same as 0.545. So would it be unusual for me to select 2 regular sodas from the 12-pack? Well, no, not for this problem. So I've got more than a 50% chance that both would contain regular soda. And by the way, I bought a regular soda 12-pack to begin with, so it wouldn't be surprising to me if I got regular soda, right? By the way, if the probability is an extremely high probability or an extremely low probability, then I would look at cases where it'd be unusual or not. Okay, and usually if it's within 5%, then I look at whether that would be unusual or not. Okay, so this would not be unusual. Part C. This says determine the probability that exactly one is diet and the other is regular. Okay, so I could select a diet first and the regular second, or I could select a regular first and then diet second, right? Either one of these two cases means that I got a diet soda and then a regular soda. Okay, or is a key word, by the way, and they did not say the word or anywhere in this problem, right? That's something I got to think of on my own. And so or means add. Add these two probabilities together. The probability of getting a diet first and the regular second. So there's 3 out of the 12 cans are diet soda. And once I pull the can from the 12-pack, there's 11 cans left in the pack. All the regular sodas are still there, though, right? All 9 of them. So I multiply by 9 over 11. Plus 9 over 12 would be the probability that I get a regular soda. And then once I select a regular soda from the 12-pack, there's 11 cans left in the 12-pack. All the diet sodas are still there, though, all 3 of them. Okay, so I multiply by 3 over 11. 3 over 12 is 1/4. 9 over 11 times 1/4 would be 9 over 44. Times plus another 9 over 44. All I've done is switch the numerators here. And 9 over 44 plus 9 over 44 gives me 18 over 44. 18 divided by 44 reduces to 9 over 22. Okay, so 9 over 22 would be the answer to that. By the way, so another way to do this problem, and I'm not sure it'd be any easier or anything like that, but I could use the complement rule. So if I want to look at the ways to select one diet and one regular, well, that means that they're both not going to be diet and they're both not going to be regular. So I could use the complement rule and take 1 minus the sum of these two answers. Okay, I'd still get the same thing. Okay, because if they're both not going to be diet and they're both not going to be regular, then one is diet, one is regular, right? Or one is regular, one is diet. Problem 29 says, according to the Bureau of Labor Statistics, there's a 5.2% probability that a randomly selected employed individual has more than one job, that's a multiple job holder, or also there is a 50.4% probability that a randomly selected employed individual is male given that he has more than one job. Okay, what is the probability that a randomly selected employed individual is a multiple job holder and male? Would it be unusual then for this to occur? Well, the probability of selecting a multiple job holder and that person is male, okay, I've written that down, would be where I use the multiplication rule. Okay, so here it is for A and B, right? So I guess I say the probability of selecting a multiple job holder times the probability of selecting a male given that person is a multiple job holder. Okay, and they've told me these two probabilities here in the story problem. So there's a 5.2% probability that a randomly selected employed individual has more than one job, it's a multiple job holder. So the probability of that happening would be 0.052. And then also there's a 50.4% probability that a randomly selected employed individual is male given that he has more than one job. Okay. So, and by the way, a mistake that I would sometimes see in class with this is that a student would write the probability of a multiple job holder times the probability of male. That's not what we want, right? So we want the probability that the person is a male given that they have more than one job, right? A conditional probability means that your sample space is reduced in size. Okay, we'll look at that a bit later. But so anyway, it is very important that I say the words given, multiple job holder. If I didn't say that, I mean, I'm not told that the probability of selecting a male in the group, so that would be wrong. 0.052 times 0.504 is roughly 0.026. So would that be unusual then, if somebody were to select a person that is a multiple job holder and male? Okay, well, yeah, I think that'd be very unusual, right? I have less than a 3% chance of that occurring. So it's likely not to happen, okay? And of course, if it did happen, it'd be kind of unusual, okay? One of the terms that we'll need to know here is called independent events. And it says that two events A and B are independent if the occurrence of event A in a probability experiment does not affect the probability of B. Two events A and B are dependent if the occurrence of A does affect the probability of B. As a note, to define independence using conditional probabilities, we write that the two events A and B are independent if the probability of A given B is equal to the probability of A, or the probability of B given A is equal to the probability of B. So just because you're given event B, that doesn't matter, right? If I find the probability of A, I'll get the same information as I was given this useless information. Or just because I was given event A, that doesn't matter, okay? If I find the probability of B, I'll get the same information, or I'll get the same result, based on whether I was given this information or not. Okay. We'll look at that later. Problem 30 says determine whether the events A and B are independent or dependent. Okay, so event A is the event that you earn $50,000 in a year, and event B is the event that you were born in December. So, do I have independent events or not? Just because I earn $50,000 in a year, that has nothing to do with the month that I was born in, right? Or just because I'm born in December, that has nothing to do with the amount of money that I'll make in a given year. Okay, so because the occurrence of one event does not affect the probability of the other event, I would conclude that this is independent. Problem 31 says that you earn an A on the next statistics test, and event B is the event that you study for the next statistics test. Okay, that would be an example of dependent events. Okay, because if I earn an A on the next test, it might be because I studied for the test. Or if I study for the test, it might have a direct effect over what letter grade I get on the test. Okay, so one could directly affect the other in terms of probability. So that's why I have dependent events there in problem 31. There's a caution statement below saying that independent events are different from mutually exclusive events. Okay, sometimes students get these terms confused. Don't do that. Okay, these are two totally different things, right? So independence means that the occurrence of event A in a probability experiment does not affect the probability of B. Okay, that's different from mutually exclusive, because mutually exclusive just means that the two events cannot happen at the same time, right? It's impossible for the two events to happen at the same time. That's different from what I'm saying up here. Okay, so don't get those two terms confused. Problem 32 is where they want us to draw a Venn diagram for problem 30, and this illustration will be an example of the caution statement given above. Okay, so well, let's see. So here's event A, and here's event B, and I've got my Venn diagram. Anyone that earns $50,000 in a year is going to be an event A, and anyone that's born in December is going to be an event B. Okay. Now there would be people in the overlap, right? In other words, there are people in the world who earn $50,000 in a year and are also born in December. So because these two events can occur at the same time, that makes them not mutually exclusive. Okay? There's another note, which is important. If two events are mutually exclusive, then they are also dependent. Let's look at that. So problem 33, they want us to draw a Venn diagram to show the possibilities for the day of July 4th, 2030. This illustration will be an example of the note given above. Okay, so I've got this Venn diagram here, and I'm talking about the day of July 4th, 2030. Okay, so it can happen on a Monday, a Tuesday, a Wednesday, a Thursday, right? And by the way, I don't want these to overlap, right? Because days don't overlap. So now clearly, I've got mutually exclusive events, right? So if July 4th, 2030 falls on Monday, it cannot fall on Wednesday or Thursday or Friday, or, any of the other 6 days. Okay. Now, why are these dependent events? Well, dependent events means that the occurrence of one event does affect the probability of the second event. Okay, so if I know that July 4th, 2030 falls on Monday, that has a direct effect over what I know about the other 6 days, and that July 4th, 2030, that holiday does not land on any of the other 6 days. Okay, so that's why they'd be dependent. Okay, and mutually exclusive events are always dependent. Okay. All right. We'll go ahead and stop the video right there in the notes, and I'll pick up with the next one then.